Hello everyone, this is the second part to my previous video about this research project around transformers, and today we're going to be going through the process of fine-tuning. Specifically, what we're going to be doing today, guys, a couple of things to be honest. First, I'm going to be telling you what the fine-tuning process is. Why would one ever want to go through such a rigorous process at all, and when is it applicable to do that? I'm going to be outlining prerequisites, points of consideration before you even begin. You can't do ML, you can't even think about fine-tuning until you have evaluation. So I'm going to be showing some of the evaluation methods that I use in my research, other ones that exist, other people use in bigger researches. Okay, so we're going to be doing that too. And then, as the title suggests, it's an evolution of fine-tuning I'm going to be talking about. So we're going to be going from smaller models to up to the top, not the largest ones ever, but to the reasonable size. Okay, so, and to address those larger models, you need proper optimization methods in place. So I'm going to show you what I used in particular, how I use it, what I experimented about them, demos, which will take part of the majority of this video because I got to break it down for you guys, okay? There are tools exist that could simplify the overall process of fine-tuning, okay? And I'll just name them for you guys that are some of the popular ones out there, but I didn't use those because I want to understand the process better on the fundamental level. So we're going to be working in notebooks for the matter. And finally, we'll see a few real-world examples to have some fun in the end. Without further ado, let's get started. It's known by the fact that fine-tuning improves the overall model performance. What's worth mentioning, though, is that it improves performance on a specific task or a series of tasks within a certain domain. Some well-known vendors like OpenAI, Microsoft, Google, they present it as adjusting their chatbot applications to the examples you send them to. But it doesn't have to be about data all the time. Sometimes if you deal with open source models like Llama, for instance, you can just follow the same process because it's published, it's known, it's in the notebooks. And you can, after introducing your own evaluation scheme where you optimize your certain metrics, you can just fine-tune hyperparameters a little so that it performs better for your case. All right? Sometimes if you are trying to generalize model better, you can play around with regularization methods a little, because what they do is that they introduce a little bit of an error to the loss function with the purpose of improving generalization. Okay. I also saw some of the examples when the folks just augment the existing data set with their own examples and go through the fine-tuning process again, which in fact improves the performance as well. Now, what is the deal here? How can you sell it? Like I already said a dozen of times, it improves performance on various tasks. And that would be known as a functional requirement from the architectural standpoint. There are a few non-functional ones you should be aware of. By choosing a model of a smaller size with fewer number of parameters, it would take less memory for you to train it, to fine-tune it. It would take less advanced hardware, GPU in particular, to go through that rigorous process. It'll also improve inference speed in terms of number of tokens per second and smaller latency, which your customers will be very appreciative of You'll also save costs on the total number of tokens processed if you own that pricing model using SaaS offering, for instance. And if you serve the model yourself, you then will save money on the infrastructure costs by choosing less advanced hardware correspondingly. And it'll also be simpler from the operational standpoint because it's much easier to deal with smaller models than with their larger counterparts. Some people do that for a reason that they don't want to put a lot of examples in the prompt. Again, increase of costs, more tokens, but also sometimes models just have a limited context window so that you can't kind of fit all of the examples in a single prompt. It's better to fine tune it then. Don't you agree? Now, when is it not the right time to fine tune? Let's talk about that. I should have started there, but I haven't, and now I feel bad about it. So let me fix that. Let me catch you up, okay? Have you tried other methods first? What about a regular prompt engineering? Have you tried that one? Oftentimes you don't really have a choice but do it. That's where you start, okay? By doing experimentation, trying various prompts, providing the model with different examples. Could take you far, could make a big difference and reveal a lot of things for you. And in fact, those larger models that ChatGPT is backed with, those excel at few shots learning, even one-shot learning, so it could work. The second step you want to take is a RAG. RAG stands for Retrieval Augmented Generation. And there are numerous variations of one you can look for in the internet, but it all comes down to retrieving a relevant context for your query, okay? These two methods come at the expense of additional tokens that will result in larger cost correspondingly. So you should be aware of that. And you should be thinking about how much usage it is that you're having in your product, how many customers, and how often they're prompting the model, okay? Very important. But if it isn't a large usage, then, and if you are looking for exposing the model to more examples for some reason, you can just consider larger models really. And before you go after fine-tuning, always ask yourself a couple of questions first, guys. Have you considered other models that are out there that are instruction tuned on the tasks that you're doing? Like maybe they will work well for you. You can even check some SaaS providers that offer that. Does the pricing work for you? Okay. Do you understand model performance? Is there an evaluation procedure in place? Are you going to optimize for certain metrics when fine-tuning? Okay. How often does your data change? Because if it changes frequently, then you're going to have to fine-tune the model very often, which will come at a price. Again, how much your use case sensitive to the context is another good question to ask, because after fine-tuning, all the knowledge is kind of lost in the parameters, right? So the model could pick up the wrong pieces during inference. And in those cases, you would want to bring them back to the context. Maybe fine-tuning is not the right choice here. Ask yourself if you rely on any prior learning that the model have gone through, especially for more journalistic use cases like chatbot apps, okay? Because if you overly fine-tune the model, it could forget a couple of things. The phenomenon is known as catastrophic forgetting in the research community. And lastly, do you fully understand the amount of complexity and effort and cost involved? For you to understand the full potential behind fine-tuning, you need to be aware of this. This is one of the good works of OpenAI from the old days, prior to when they released ChatGPT to the world in November of 2022. They had done a lot of experiments with their initial GPT-3 model so that it became GPT 3.5 that has been powering ChatGPT ever since. The way they made this transition is that they fine-tuned it specifically for instruction following. But even prior to that, they figured that supervised fine-tuning that what we are about to see in my demo significantly improves the performance already compared with this initial pre-trained model. So we've got that, but they've also made it one step further by leveraging reinforcement learning with human feedback. They've collected a bunch of data and they put raters together to rate the potential responses in certain order, and they train their reward model through which they train their policy model, and they use that in turn to fine-tune their final instruct GPT model that, as you can see on the chart, like even smaller models, like with much fewer, 100 times fewer parameters, significantly outperform the original model. That has been a great achievement. Now when we know that we want to do fine-tuning, the question becomes how? And that would be a very good question. Remember the time when I mentioned that such a procedure would definitely involve some cost and effort? Here's what I meant by that. This section, hopefully, that we've approached just now, is going to start revealing some truth for you guys. And that would mean putting in some work involving both research and development, including coding, working in notebooks, exploring some GitHub repositories, writing some code, or running some code on the appropriate hardware, and that hardware is needed to be found amongst various cloud or SaaS providers that is appropriate for your particular case, for your wallet. Okay, let's take it step by step. The first thing you want to ask yourself is, what do you have as of now? What's model baseline performance? What data gets through it? How much data gets processed? At what speed? What amount of usage do you have in production? How many users are using your thing? How often? What number of tokens gets processed in a period of time? Do you want to improve any of those things? And for how much? Then you're going to need to define the requirements, understand the constraints, like hardware constraints you have in your possession or in the cloud, time and budget resources you have, number of operational personnel capable of doing that with the required skill level. You need to understand the model size you're aiming for, what is the high quality training data you have to fine-tune the model on, what is the desired performance, what are the numbers, the metrics are you aiming for, you're going to optimize for, what is this minimum context window you're going to be satisfied with. Next, consider a base model or better multiple models that will be good candidates for your case that you'll be optimizing for your thing. Explore their architecture, understand their layer structure, check out inputs and outputs. See if there has been anyone who has managed to successfully fine-tune those models on a similar task successfully, reporting about it. And then there is a big thing, which is performance evaluation process. Have you done that? Ask yourself, is the process already in place, fully functional, tested and executed on a data set? In fact, do you have a high quality data set for that? Are you collecting the metrics and storing somewhere in a database or organized files? Do you know how to do the analysis of that? Next, you're going to figure out computational resources that you're going to need for your quest. How much of it do you in fact need? What do you already have? What you could potentially get from virtually anyone, whether it's service cloud provider or SaaS vendor, as long as they give you what you need for the desired price, you should be good, I think. Next, I want to suggest you automate and test everything properly. And by everything, I mean your entire fine-tuning procedure, but on a smaller data set and using a lighter hardware. Because you don't want to be doing troubleshooting in the cloud on a very heavy and expensive instance or even a cluster of such, because it's going to be expensive again and not quite sustainable. Which brings us to arguably the most important part of this process, which is evaluation. You need to understand it well before you even start. I'm going to try to explain it to you on the high level, and I'll show you some of the specific techniques that I used in my research later in the demo section. There are well-known frameworks such as Helm and GPT-4All everybody is using these days to test their models and fine-tuned version of those models to compete with each other for a place on a leadership board. Those frameworks also come with a full evaluation harness provided in their GitHub repositories, where you can also find all of the scripts, instructions for you to repeat, to go through the procedure for your particular model, to bring the results to the leadership board as well. Those frameworks utilize a number of scenarios to test the models against each other in similar conditions. Some of the well-known ones are MMLU, which stands for Massive Multitask Language Understanding, and there's GSM-8K, which is Grade School Math or Word Problem. Those scenarios basically represent multi-choice questions in multiple language domains to challenge models on various language aspects, but they output the result in a consolidated score, which is brought back up to the leadership board for a simple comparison. But it all sort of comes down to the metrics, which we're going to be exploring more. I used in my research. I'm going to be showing to you in the demo. If the first two methods are good for sort of comparing general model capabilities, working with and understanding language, the metrics, in fact, are better to compare models' capabilities on the specific tasks. These three scores, Blue, Rouge, and Meteor, work well for various language tasks. Let me just give you an example. Perhaps it'll help to understand it better. For instance, you've got a model, and that is a sequence-to-sequence model using for a translation task, let's say. So you're sending a text of one language to the input of the model. The text of another language is produced from the output. But for evaluation, you will also need references, sometimes referred as labels. Those are the desired texts you're expecting the model to produce ideally. More often than not, texts differ, like desired texts, references, and actual output refer, but not significantly. So the metrics help to kind of understand for how much. And if you do it at scale on the entire evaluation data set, which would normally contain about 1,000 or even more samples, it will give you a relative understanding how well the model has performed. Okay? Perplexity is a little harder than that, but we should understand it too, because it's majorly used for fine-tuning, and you can also use it for evaluation, provided that you're gonna be comparing different versions of the same model with the same tokenizer. And here's why. Hugging Face has a good page about it. They say that you can think of it as an evaluation of the model's ability to predict uniformly among the set of specified tokens in the corpus. And they also say that tokenizer actually plays a big role in that. That's why you can't kind of compare scores from different tokenizers, okay? So it can be thought as an algorithm as well, over with a sliding window over a sequence that we are calculating the score against, okay? This is basically cross entropy, which is a function of the distribution of the output sequence that we are getting out of the model relative to a distribution of the reference sequence we are expecting the model produce with an expected value. Okay, so we're basically doing this like in an iterative process over the entire sequence and calculating that score, and then the mean value of all of the collected data points is going to give you the perplexity score. Finally, what you can also do to evaluate your model is that you can make use of a bunch of online services available, such as Discord bot, for instance, by Neural PS. I think they put it together for one of their hackathons, competitions, so to speak. There is always a Hugging Face Hub where they provide you with an instruction how to send the evaluation job. And Vertex AI has something in place as well, but it will all take you to kind of define the, playing by their rules, defining the task, evaluation task, preparing the data set, sending it for an execution. It'll still take some work, whether you want it or not. Finally, before we do the demo, I want to cover this last important topic, because chances are that as you keep exploring it, you would likely want to use bigger, more capable models that would not quite meet your hardware constraints. So that you will have to think about some optimization techniques. And there are a few of them that I use that I am aware of. So let's have a look. Quantization is a technique of decreasing memory footprint of the model for inference and training procedures. It is achieved by reducing the precision of the model's weights and activations to a lower bit width. So instead of using 32-bit floating point, you're going to be using like 16-bit or 7 or even 4. There are methods that you can use that will allow you to achieve that on the fly as you download the model, such as bits and bytes, whereas other methods will require you to pre-process the model in advance. Various parameter efficient fine-tuning methods such as Lora, QLora, AdaLora will help you avoid training all of the parameters of those large models, because that is simply not possible on regular consumer hardware or even some capable GPUs such as H100 and A100 with 80 gigabyte of memory, because the model will just simply not fit there. So these methods will allow you to train just a small portion of all of the parameters through introduced adapters within the model's layers, as you can see in the picture here, mostly for those linear layers. So you're going to be freezing the rest of the parameters that the model has, and you're going to be only focusing on these like Lora linear blocks and training the parameters there. Okay. All right, guys, we're getting closer to the gist of all of it: actual code, implementation, logic expressed in the notebooks with the relevant results. As you can see here, I've gone through quite a bit of experimentation trying to fine-tune different models of various architecture types, starting with small transformers, ending up with larger language models. I'll limit myself to just the models up to 10 billion parameters, because fine-tuning and training models even larger than that would have taken quite a bit of effort, and it's totally different type of problem to address. So we're not going to be doing it. Neither am I going to be going through all of the examples I have here. I'll share all of it with you, though. You can find code probably in my GitHub repository. I'll make sure it's available by the time I release this video. I figured that I want to narrow down the number of models. I want to show you the process of fine-tuning around of. And those are the models gonna be good representatives of various transformers of different type and size. As per result of my research, which you can learn more about from my previous video, where I'm in fact concluding that T5 model is the best choice for this particular language task. So we're gonna be breaking down that one. On top of that, I've selected GPT-2 while being the kind of initial successful decoder-only transformer, which other currently known large language models even have borrowed on the idea of. So given the simplicity of one and the small size, I conclude that it's a good example for us to play around in various kind of combinations, in various settings, the expertise, the knowledge of which you can apply for larger transformers, for small language models like Phi2 and Llama 2 billion, which a little bit better from the performance standpoint than GPT-2, as you can see in the picture for a reason. And lastly, the model that's missing here, I also wanted to show you, is Llama 2 7 billion parameters. That is the largest one I'm fine-tuning. And since it's that big, it just doesn't simply fit into regular consumer hardware. So I have to come up with a bunch of optimization methods that would allow me to achieve similar results after the fine-tuning. Here we have it, the very first notebook with fine-tuning of the T5 model. We're going to go through it cell by cell. In the very first cell, I am loading a bunch of extensions. I am authenticating against a Hugging Face to be able to upload the models. That is the essential goal at the end of this exercise. I'm authenticating using this token. The token is stored in the and file in my root directory, and the way it gets into the Jupyter environment is through this, using this extension. Next, what we're doing is that we're installing a bunch of dependencies. We only need it once. That's why you see this skip command, basically, so that I don't waste time. Every next time I run the entire notebook, for instance, to retrain the model, I essentially need to reset the memory. That's why I need to restart the notebook to start anew, fresh. So this only needs to be executed once. You can also do it outside of your environment as well. I'm using Conda for that. So Conda is this sort of a Python sandbox environment where you can have like multiple such sandboxes and install independent kind of different dependencies into each and every one of them. Quite convenient. Next is just a bunch of import statements of what I'm going to essentially be using down the notebook. I'm importing packages as well as specific classes or even functions of those packages. But I'm also importing my own functions. That is one of the ways to abstract kind of a few things out of the notebooks and reuse them in a repetitive manner across all of your training notebooks. That's what I've done here. Anyway, this is a separate package called utils, and in there you can see a bunch of Python files that with like data sets and various functions, and that I'm importing here, right here, for the further use in this particular notebook and other notebooks. Though I wouldn't say that is a recommended practice, as you could probably see or will learn if you get down the path of Hugging Face community. That will teach you the way that they support their libraries, that by actually over repeating themselves. They don't mind doing that, and they think that it just basically allows you to keep the clean code, understandable code, in fact, in individual files. So less abstraction is better for them. That's why I wouldn't recommend strongly using this very approach. Anyway, I haven't used it much, as you will probably learn later down in the notebook. In fact, I reconsidered that after learning about this Hugging Face mantra. I guess I just have this software engineering ingenuity of trying to abstract everything away, so for the sake of simplicity. So, but I get that we gonna be following the standard path. That's why you will probably find all of the details in a single notebook sufficient to finish the training. In the next cell, I'm loading the model itself as well as its tokenizer. I'm also specifying a few standard variables that I'm going to be using a lot in this notebook as well as other ones. I've done that for the sake of standardization in accordance with what community in fact uses. You can also see that I'm printing out a few data points about those loaded assets to confirm that I'm on the right path. Specifically, I am clarifying the model type, the tokenizer type, as well as the model type, which is correspondingly printed out in these two lines. Okay. And I'm also printing out the model config, which is a very important asset for the model because it influences the overall model behavior as well as performance. In fact, it comes with the model itself, and you can see it, you can find it in the Hugging Face repository if you switch to the file section and open up this config.json file. It's going to be all here, though interesting to mention is that sometimes, in fact, you would need to change a couple of things about that if you follow down a specific fine-tuning path. The next section is a standard one of loading a data set for which I'm using Grammarly dataset for the sake of this research. That's already actually prepared for fine-tuning and evaluation. This is a standard section that you'll see in all my other fine-tuning notebooks as well, with a few slight changes needed to address some uniquenesses of the models of different types. In particular, the biggest difference in terms of inputs and outputs when it comes to the models of different types is going to be between encoder-decoder type of model and decoder-only model, in that encoder-decoder models accept one sequence in the input and produce another sequence that has nothing to do with its initial first input sequence in the output. Whereas decoder-only models, they just take the input sequence and sort of just produce the larger version of the same sequence. So you have to kind of pre-process inputs properly for fine-tuning, as well as like post-process the outputs correspondingly to trim that initial portion of that larger sequence for the decoder-only models. As you can see here, in my preparing the data set, after I'm downloading it from the Hugging Face registry, I'm sort of willing to control what portion of the data set is going to be used in the training procedure. And that is because I don't want to kind of go all in on it straight away until I figure the proper hyperparameters so that I am maxing out the capabilities of my hardware. I've established the proper kind of batch sizes, the lock steps, and all that is an evaluation procedure, so to speak. So the initial attempt is to make it stable on a smaller portion of that data set, and then once that's successful, I'm going to simply increase it to the full extent. One of the transformations that I'm doing around this data set is that I'm reprocessing subsets of a particular task, and then combining them back again after conducting a split into a different kind of training set. So if you have a look into the data set itself, you can do it in Hugging Face using the viewer. Okay, you can see what the data set represents basically, right? These are the inputs and references, so to speak, or labels. And they also have this additional column of feature that determines a task. The inputs and references format remains the same, whereas the task just an additional like category, and there are many of them. There's clarity task, for instance, and there's GSC, which is a grammar task, which stands for grammar. So the purpose of these is to determine how well the model performs on a variety of language tasks when it comes to different challenges. I'm doing exactly that because I've noticed that it hasn't been evenly distributed in the initial split. So I'm recombining those subsets again, doing the split on each and every subset of such tasks so that it's, again, evenly distributed and the test is more clear. Another thing I'm doing is that I'm determining the maximum length of the biggest sequence amongst all of the sequences comprising the data set, both for training and testing purposes. I'm doing that to make sure that those large sequences aren't going to exceed the maximum context window that the model has, as well as it does not pass the threshold of the various limitations I'm imposing onto the tokenizer and generator as well. The next couple of things here I'm doing is that I am converting that final data set into a different structure of a dictionary type, with the key being the task, so that I can see how many samples comprise a particular task. And also, to be honest, for the simplicity of retrieval of those individual samples of particular tasks for a quick smoke test. This next section is going to be an important one, so listen carefully. Those high-level fine-tuning tools probably not going to give you this level of detail, so I'm going to reveal it for you. So you better prepare for a better challenge. The task here is to convert data set that we already have, that we just put together, into another data set for fine-tuning purposes, but the data points of which gonna be numeric representations, because we remember, right, models don't work with textual representations. They accept numbers and they produce numbers, and those are called tokenized sequences consisting of numbers. Okay, tokenizer is this thing that comes with the model that the model pre-trained with, that you're going to be using for fine-tuning as well as it's used for inference purposes. It's an essential part of the model. It takes a textual representation of a sequence and produces a vector, numeric representation of such. It has vocabulary, and it does it in a elaborate way. We're not gonna break it down. It just accept it as it is at the moment for the simplicity's sake. The way I do it here is that I'm taking the data set and I'm applying this map function of a process data set in batch. Okay, there's a batch so that I am not like exceeding my memory limits or so. I believe these are processed on these are processed on my CPU. So I have a little bit more power there and it's not like very heavy task. We're not like processing all of the model's parameters. We're just tokenizing textual sequences. We're doing it for two fields in our data set, for the inputs and for the references. Okay, remember, sequence to sequence model, it accepts one sequence, which in case of a grammar test is gonna be the prefix of a challenge, like fix this grammar, for instance, right? And the sentence, for instance, right? So like fix this grammar with some incorrect sentence gonna be our input of a one sample, and the reference is gonna be the result of it. So we have this data set where we have a task challenge and we have a reference, what we're trying to optimize for, which we're going to train the model to optimize for essentially. And that's what we are converting here into model inputs and labels. Labels is a standard name, which you'll see in each and every Hugging Face library probably. So these are the standard names, so I have to name it similarly. And there's one more field that comes up in the resultant data set we're going to be using for fine-tuning, which is attention mask. That is to restrict the model to access every single token in a sequence, cause remember those come out in batches. So we want a model to limit from attaining all of the tokens that don't bear any meaning in a sequence. Okay. Hopefully this view will help to clarify a few things for you guys. What I'm doing here is I'm printing out the tokenized version of a sequence of a single sample that is coded right here of that processed data set, okay? And it comes out like this. The numbers identify different tokens that could comprise either a word or a portion of a word. 0 tokens has no meanings. That is to signal to the model to kind of skip them. The second row shows the attention mask, where with ones and zeros, whereas ones signify that the model's attention block has to attend corresponding tokens on the same position, whereas zeros just tell it to completely skip those tokens, which makes sense given the zeros in the input sequence as well. The third row is what we are expecting the model to produce. These are the tokenized sequence of the reference text with a lesser length, which is possible with sequence-to-sequence models, and which is not with a decoder-only model, which we will learn later. It's also worth explaining this second block here that comes right below. That is a result of a data collator, which is in fact what trainer uses for fine-tuning. It does that through data loader, which I'm creating here as well, with a very small batch size of 2 for debugging reasons. And I'm printing out the very first item coming out of it. That's what we see here in the output section, which reminds us about the previous data structure we saw after the plain processing, with a few differences though. That the elements now tensors over the plain list Python data types, which allows us to send it directly to the CUDA device for processing. They also come in batches of a size of 2, since we specified it specifically. The data loader also makes sure that all those sequences in a batch come with the same size by adding special path tokens that bear no meaning, but allowing this to be sent to CUDA. CUDA only works with like matrices of the same size. We are approaching the training section, where I'm setting up a few variables for further usage. I'm printing out utilization numbers, mostly for GPU memory, how much it's used overall, as well as how much CUDA is leveraging, how much it has reserved so far, and a little bit of a RAM to see how things are with that. I'm using this external function that is sitting in this separate package, utils package. I'm also setting up memory fraction explicitly because I'm doing training on the Windows machine, and Windows tends to leverage this virtual memory as an extension to GPU memory. It works okay for the games, but for fine-tuning and training, when things get there, it becomes very slow. So I want to intentionally avoid that, so I'm specifying it here for PyTorch library to guide on where it should exit out with a out of memory error if the memory is occupied beyond that point. And I'm also printing out the number of parameters that we are going to train for this particular model. Next section is interesting. That is where I'm specifying a few metrics and I'm making use of them for evaluation reasons. You don't have to, in fact, use any metrics during fine-tuning because the trainer is going to be relying on a loss function of the model, which in turn uses perplexity, or in other words, cross entropy. But I'm doing it regardless because I want to see how things improve over time as I'm doing fine-tuning. I want to see how much the predictions have become better every next portion of the steps. This comes as a function that gets triggered during evaluation, providing predictions and labels. And then I'm doing this, the processing of those by extracting actual textual representation from the tokens, from the output tokens, predictions and labels correspondingly. And I'm calculating the scores correspondingly and saving it in the final data structure, sending back to the evaluator for it to report on the graph, on the chart. The next small section here is how I launch TensorBoard, which is a visualization tool for various metrics. As metrics get registered during fine-tuning, they will be displayed dynamically, presenting their actual value as things improve over time. The most important metric you'll be seeing there regardless is a loss. There will be one chart dedicated to it, but you can also bring other metrics, whatever you wish really, that you calculate in your evaluation function, what I've done here in particular. The next thing here is a calculation of how many steps the trainer will have to go through to finish the entire data set of items. Given the batch size and using this feature known as gradient accumulation steps, you are calculating the number of steps per epoch, and the epoch is going to be the one cycle of fine-tuning on the entire data set. Mostly you need these two exposed in order to determine optimal values that meet your hardware requirements. For instance, for me, I did the training on my local hardware equipped with GTX 3080 with 10 gigabytes of memory, and on the remote hardware as well, equipped with 800 with 80 gigabytes of memory, so 8 times larger than that. So I had to play around with these settings quite a bit to max out the full potential of GPU available. And then you define the trainer as well as its parameters. There are a bunch of things you'll see virtually everywhere. They are set up in an optimal way for this particular model. A few things worth mentioning: the steps categories. These are how often I am logging or registering the loss metric, how often I'm doing evaluation, in fact, and how often I want to save the model. It's called checkpointing. For instance, if when I've established the optimal hyperparameters on a portion of a data set, I'm going to be doing the entire full data set next time. So I want to save a few intermediate models just in case this like training work gets interrupted, which could be the case given that I'm doing it on a spot instance. And in case it does get interrupted, all I have to do next time I launch it is I'm gonna uncomment this previous line here so that the trainer knows that it has to take that latest endpoint to continue training on. And then after you initiate the training, it'll take quite a bit of time depending on the size of your data set and the number of times you want to iterate over it, number of epochs, in other words. Things will get registered as you go, such as the training loss, which will keep reducing as this is what you are optimizing for, as well as other metrics that you calculate in your evaluation function I showed earlier. Finally, when you're done, you want to save the model to the POP because it's like heavy, and Hugging Face provides you with a free storage option, either private or public, shared with everybody. I recommend doing that. I also recommend saving your notebook straight away into the GitHub repository so that you can synchronize the notebook on different machines. And then I'm doing the inference test of the trained model just to see whether it's started producing something meaningful that can be perceived and estimated by a human eye. Given that the initial model was a pre-trained version of T5, it did not produce anything meaningful input whatsoever. And here we are seeing the drastic improvement on these very tasks. The next thing we're going to be going through as a natural progression in this evolution journey is a GPT-2 model with a classic decoder-only architecture with a relatively small number of parameters compared with the small language models. I'm only going to show you differences compared with the T5 model we just explored in this very notebook. Contrary to the T5 model, we are doing a little bit of a customization here for tokenizer. We are setting it up so that it adds this end of sequence token whenever it processes the sequence. We are also specifying the path token equal to end of sequence token. It doesn't really matter for the training reasons. And we also setting the padding side to left, which is typical for decoder-only models. We are printing all of these things out to confirm that they are what you want them to be. We are loading the model correspondingly, printing out its type. You see, I'm using these auto functions here. So I want to know what exactly the class that this function has retrieved for me for this particular model. Hugging Face has this like abstraction functions for retrieving models, for instance, where they determine out of the specific names what kind of class the model to instantiate with. And I'm also printing out generation, config, and the model structure itself to get familiar with, really. This is the output that comes out as I'm printing it out. The generation config doesn't really have much, only the tokens that I specify explicitly. The concept of using generation config becomes popular after decoder-only models gain popularity with an arrival of such models as Llama and Mistral. Hugging Face team has realized that, well, we want to kind of abstract this very notion of generating sequences into another concept. There is a generator class that can help with that, and it relies on this generation config to configure the underlying tokenizer. The block after that represents the model architecture. This is a typical decoder-only architecture consisting of a few layers of embeddings, the attention block, the feed-forward multi-layer perception block. They use it for the model to better detect and determine data patterns. And the final linear layer for the model head. Next, we're preparing the data set similar to what we've done with T5, with the only difference that we're adding these two additional fields here, the request and the prompt fields. The simple way to think about it as if you are working with ChatGPT. Remember, when you interact with ChatGPT, you give it the context and then you ask something from it. Similar to that, we are giving the model the input. In our case, that is the grammar task to correct the sentence, and the sentence itself that is sitting in this input field. And we're also adding the suffix here, a particular word response, to train the model to expect it before it starts predicting the consequent sequence, okay? So we're going to be using these two fields to train the model on. This is another important block, how we prepare a data set. It significantly differs from what we've done with T5, so pay close attention. we're processing the data set through map using this function in batches of 10. We are relying on those additional fields we just added, and we're tokenizing them first, and then iterating over them one by one. In this for block, they come as individual sequences of tokens over single kind of sentence. Okay. The goal here is to determine labels, because the labels are gonna be that they're not gonna cover the entire sequence, but only the portion of it that the model has to predict from the entire reference sequence. Okay, so we're kind of we're calculating how many tokens we should ignore in the beginning, and then adding the tokens equal to the length of the rest of the sequence. We are also calculating the mask, and we are most importantly adding this end of sequence token everywhere for the labels, for the inputs, and we're also adding it for the attention mask for the model to train on when to end the sequence in its prediction. I'm also printing out the output from data collator to confirm that it's done the job properly, that the logic is defined in the right way. And here how it looks like. We're only going to explore this block below. Similar to the T5 view, we're having like two items in a batch here. For the input IDs, remember we specified the padding side to the left. So there's a bunch of similar tokens on the left side now that are preceding the normal tokens that bear the meaning in the beginning of the sequence. In fact, 50 to 56 is a token number for padding and for the end of the sequence. We do the same thing to the attention mask, making the model ignore all these like initial tokens in the sequence of a second item. And we're adding this same thing, same end of sequence token in the end, in order for the model to train on when to end the sequence in its prediction. And we're also calculating the labels, which is super important in fact. That is what we are going to train the model to predict at the end of the day. So the labels, they only cover the portion of the tokens that we are trying to predict. Like everything that comes after that key response word, if you remember, we specified in the prompt. Then I'm doing a little bit of a test to see how the base model performs before it undergoes fine-tuning. I'm doing it for a single task for a few items in a batch. And I'm printing out a couple of details here. First, the actual request that goes onto the input of this generate function. And I'm just simply challenging the model to make this sentence simple, okay? I'm also printing out the reference to kind of see whether the model is anywhere close to what is expected from it. And what it prints out is a lot of stuff that is nowhere near what we are expecting it to do, okay? And it's what's worth mentioning is that it does not know when to end the sequence. So it keeps printing until the maximum length of tokens I specify here for the generate function. Next, we're preparing for the training in the similar vein. And then we're defining the evaluation function a bit differently though, in a sense that we are preprocessing those retrieved predicted values, or substituting the negative tokens because they cannot be interpreted properly by tokenizer. So we are changing them with the path token for predictions and labels. And then we're retrieving textual representations of those things to send to the metrics, okay? We're computing the metrics similarly, reporting back on them. This next function define is important. That is what we specify for the trainer as a preprocessed logics for metrics function. it gets executed every time that the trainer sends a batch of samples for evaluation. And if you don't do that, this stuff would keep accumulating, eventually resulting in a memory leak. As long as you have enough memory, it should not be a big deal, but if the evaluation set is big enough, you can just as well end up with a out-of-memory problem. This function helps to avoid that by trimming the output to only latest dimension. Basically, we are calculating argmax of all of the only on the latest dimension of all of the logits and sending it to the evaluation function to do its job. And the rest of it is pretty much the same. We are estimating the number of steps, we are defining training parameters, and we initiate the training. After we've done with the training, we want to save the model to the hub, and we also want to run a quick inference test to see whether the model has started producing something meaningful. For that, we are leveraging this generate function, providing the inputs, tokenized inputs. We're specifying the max number of new tokens this time instead of the total length. And remember I mentioned, right, these generator-only models, they produce the entire sequence, like including your input. So you want to, like ideally, trim it out before you printing the result. That's what I'm doing here using the tensor data structure to make it a little bit more efficient for tokenizer, to not overload the tokenizer, and I'm printing the result. Let's explore the intermediary outputs to clarify a few aspects. That's what we are prompting the model with and expecting to produce these. Okay, these are the two tasks here. Our tokenized sequences look like this in a tensor data type with a proper attention mask, without labels though this time. And these are the outputs, and the outputs are like a full sequence, right? Including these like initial tokens. So we know what we want to do. We want to kind of trim this entire sequence out of this like initial like prefix, okay, out of this, so that in the end, we only receiving the essence, the correct grammar sentence, which we are going to use for our like a total evaluation test. Finally, let's go see what I've done with Llama 2, because that thing is quite big and has 7 billion parameters. And even GPU containing 80 gigabytes of memory is not going to help you much. If you want to do it, use it for fine-tuning in a regular manner, what we've just done with GPT-2. First thing to mention is that I'm preloading the chat version of this model that has been already instruction tuned for chat specific use cases. Next, I'm changing a few tokenizer options because that's what they are recommending to do. This is important. This is quantization config. So I essentially am loading the model in a lower precision using just 4 bits over 16 bits, what it has been trained with. By just doing this, it drops memory requirements like 4 times, which is like increases my chances to fine-tune it successfully on a limited hardware. The way I prepare the dataset differs similarly in those 2 additional fields for request and prompting. But this time I have to follow the very specific format what they used during instruction tuning for the chat use case, because I'm not going to be training all of the model's parameters leveraging Lora. So that needs to remain the same for me to not confuse the model with another format. We are improving our technique here because a better way has been established for those decoder only. So we're skipping this calculation of labels and attention masks. This is a new block where we're defining a parameter efficient fine-tuning method of Lora and really configuring some of the parameters of that. They're worth playing around with. You can treat them as hyperparameters, and changing them a little could improve situation on the case-by-case basis. There is a way to specify what models layers you want to target with those Lora adapters. And there's a way to even unfroze some of the layers of the model so that they are fully trained. The model structure, after we've converted it to Lora, is going to look like this. These are the two blocks, Lora linear layers, which we are going to be focusing on during fine-tuning, leaving the rest of the layers unchanged. And by doing that, we are significantly reducing the number of trained parameters, like down to 33 million. This is like a very, very small number of parameters, which will allow us to go through the training process relatively fast. By increasing this rank parameter, you are increasing the number of trained parameters, basically extending that Lora matrix, which could work better if you want to train the model more specifically, let's say. And this Lora alpha parameter defines how much the model should rely on the Lora layers over the original layers, basically making it biased towards your training set. This section is not going to change. We are calculating the metrics in a similar manner and printing them out. Remember that additional function to prevent from the memory leak during evaluation. TensorBoard is going to be necessary as well, estimating the number of steps overall. In the training section, we are using a supervised fine-tuning trainer this time. This is different from what we used to be doing in the sense that there's no data collator function now, because all of that is done under the hood for you. The only thing you have to specify is the data set itself, as well as the field, the prompt, remember that prompt field with the entire sequence, which is going to be taken out of the data set for the training purposes by the trainer itself in an intelligent manner. This very trainer will also take care of calculating labels and attention masks for you, as well as will set up a data collator with an appropriate batch so that you don't have to worry. The only thing you will need to think about is these regular hyperparameters. You can still define the batch size and gradient accumulation steps. You'll have to for a particular hardware requirements. Training these larger models with Lora is harder in the sense that you're not retraining all of the parameters, so you have to stick to the particular format to confuse the model. But it's also that you are taking the model, the large model that has already been fine-tuned for instruction following on a broader spectrum of tasks. So it's harder to convince the model to do one or few particular things properly. For instance, after training the model on the subset of a training sample, the model has started producing something that I'm expecting it to. But in some occasions, it's still printing out the prefixes, those that are subject for a chatbot application. That's what I was said regarding the model is biased towards chatbot application. It's not simple to get rid of it because it's in all of the rest of the parameters, as you can understand me. Probably to address this very notion, you will need to take the base model instead over the chat model and train on a larger set of examples, hoping that the model will generalize properly towards your particular task. As per the tools guys, I would really recommend looking into this one. Axolotl is quite popular these days. A lot of people using it. It's quite a gem, sort of a collection of best practices consolidated in a single place and wrapped around a convenient library and CLI interface. It supports a bunch of features, those standard models mostly, with a decoder-only classic architecture, Llama, Falcon, Mixtral, and others. Supports parameter-efficient fine-tuning methods we discovered as well. Has CLI interface. It supports other optimizations for even larger challenges if you want to train the model using distributed architecture, multiple GPUs, or even multiple, the cluster of multiple instances with several GPUs on each. So those FSDP and deep speed frameworks allow that, but the tool just simplifies the way to leverage it. It also supports additional workflows of scheduling it for fine-tuning in the cloud through Docker or by other means. I think it's quite nice, and observability features via MLflow and WAN-DB. Those are quite optimal options. They have a matrix feature supported per model. For instance, Llama is very capable, can leverage it with various techniques, optimization techniques, can enable flash attention, can make use of X-formers, whereas for Mixtral, the newest one, I think, like some of it is being implemented as of now, as we're speaking, I believe. So it's coming at some point, at some day. Llama, one of the models we also investigated, so not everything is supported just yet, which means that you either wait or really understand the concept behind it and just do it yourself with a little bit more effort. One of the fun examples I wanted to share with you guys is this. One of the researchers has figured a way to fine-tune a language model, Mixtral 7 billion, to give them recommendations for a game. This game, Magic the Gathering, is quite classic, it's popular, it's been digitized, now you can download it on your PC and play it. I think there's iOS versions available too. This is a collectible card game where you are collecting cards, you're purchasing them, you're winning them over, and you compete against like other players on the battle. The better the deck, the more chances you have in the battle, okay? There's a game mode called Draft, which where you come without prepared deck. You basically assemble the deck once before a series of battles with random players with participants. But the way it goes is that you're given like you have to assemble a deck containing like 40 cards or so, and you're given like an option to select a card out of 14, and then you iterate on it until you assemble the entire deck. So here there are like a lot of strategies how you do that in a proper manner, what cards are better to select without knowing what are coming in the future, okay? And as a result of that, 17 lands data set has been assembled containing best kind of draft cards, okay? The best collection of those draft decks. The way he's fine-tuned the model is this. He uses very prompt to interact with the model. He set up this system message to define the context for the model assistant. He used this very request every time to challenge the model to give him a recommendation by specifying what stage of that draft they are in the moment and what cards are available for a pick. And there is a query message for an assistant. He also used that data set of 7 lands to prepare another data set to train the model on a similar kind of pattern, right? Whereas the recommendation is given. So he's done that over all the iterations of that prepared data set, and received some tangible results. He's provided with these results in the form of this chart, and it seems he's been using the accuracy metric, which is probably something that was tied onto the initial data sets, because I was actually expecting a little bit more practical metric, that like a percentage of the games that a deck can compete, like can win over, right? But anyways, let's say there's an accuracy and there's like humor picker kind of excels at it, right? Compared with the automatic LLM assisted methods. But here you can also see that if you don't fine-tune the model and use a model off the shelf, and the most capable model like GPT-4 is not going to be as accurate this particular task as if you were to fine-tune the model specifically. I mean, the smallest model here, Mistral 7 billion parameters with very few examples given, right? Outperform those off-the-shelf models. This concludes my fine-tuning video. It's another long one, about an hour long, of good quality content, I hope. It has a bit of both, a good blend of theory and practice, I believe, and I'm going to be releasing a functional code as well in the repository, which you can find in the description of this video. Hopefully Google also indexes this video well, so that it is can be spotted in the search whenever somebody is trying to spot for particular things, so that they get sent to a particular piece of the video directly. And as always, I'm available on social media. If you want to discuss any of this stuff or have ideas for what you want to explore more, I might be interested to do it with you. I'm in New York City, so if you're around, just drop me a message so we can meet. I'm also an active participant of various meetup activities and planning to do a talk on one of them later this summer. So I hope to see you around, and I hope to engage. See you soon, and good luck.